Hello everyone. Here, this is Vijayalakshmi Subnalli from WinMaths. In this session, we have to discuss the concept relations and functions exercise problems 1.1. We have already discussed up to 1 to 6 questions in last session. Now, the 7th questions will be discussed here. Show that the relation are in the set A of all the books in a library of a college given by a relation R is equals to order pair x comma y. X and y have the same number of pages is an equivalence relation. Now we have to show a equivalence relation. Here, before going to prove the equivalence relation, the condition or the relation must be satisfied reflexive, symmetric and transitive conditions. Okay, the relations contain reflexive, transitive and symmetric condition. Here, in that condition, a library, main condition in library. A library of college contain lots of books. Here in this example we have to consider a particular books. Okay, first one condition will be reflexive condition. First one is reflexive condition. Here a relation R is equals to x comma x such that x and x have same number of pages. Same number of pages because we have considered a book. Okay, for example, consider a second year book. All the second year books, the first page will be the first or some particular page contain topic. All the books also contain the same number of pages. Therefore, x comma x will be satisfied the relation R. X and x are the same number of pages. Same number of pages. It is reflexive. Then, for symmetric condition, here x and y have the same number of pages. If we have to consider two books, x is one book and y is one book, belongs to R, that is relation. X has the same number of pages and y has the same number of pages. That implies y comma x is also belongs to R. Okay, x and y have the x and y have same number of pages. Same number of pages. That implies y and x have the same number of pages. It is symmetric. Again, have to consider third condition, transitivity or transitive. Here, x and y have same number of pages. Again, y and z is also another book contain a same number of pages. Okay, same number of pages. Hence, that implies first and third book, that is X and Z have same number of pages. Same number of pages. Have the same number of pages. Therefore, it is transitive. Hence the proof. Because three conditions are obvious, it is equivalence relation. Equivalence relations. Now, here the next question. Show that the relation R in the set A is equals to 1, 2, 3, 4, 5 given by R is equals to A comma B such that A minus B is even. Is an equivalence relation. Okay, is an equivalence relation. First condition, have to prove the equivalence relation for this condition. After that, show that all the elements of 1, 3, 5 are related to each other and all the elements of 2, 4 are related to each other. Okay, these type of the question will be discussed already. Okay, we discussed already. Then we have to prove now. First one is reflexive condition. We here consider a relation A comma B such that A minus B is even. First, for reflexive condition, for every A comma A, for every A comma A such that A minus B is even. Okay, A for every A comma A such that A minus B is even. Here consider A and A minus A is even. A minus A means 0. 0 is also an even number. 0 is a even number. Therefore, it is reflexive. Again, for symmetric condition. Now, consider A comma B such that A minus B is even. Okay, that implies B comma A such that A have to taken minus as a common, B minus B is even. Here we have to consider the modulus function. Mod of negative value will be again a positive value, that is B comma A such that B minus A is also an even number. Therefore, A comma B belongs to relation R and B comma A is also belongs to R. Hence, it is symmetric. Because the elements of A, the elements of set A contain 1, 2, 3, 4, 5. Have to consider 2, 4. That is, here 2 minus 4 will be minus 2, that is 2, and 4 minus 2 is also 2, is also an even integer. Again, for transitive condition. For transitive condition, here A comma B such that A minus B is even and B comma C such that B minus C is even. That implies A comma C is also even. That is A comma B belongs to R and B comma C belongs to R. That implies A comma C is also belongs to R. Therefore, it is transitive. Therefore, it is here we have to check the condition for symmetric. Now, consider 4, 8 which is belongs to R. That implies modulus of difference 4 minus 8 is multiple of 4, right? Again, and 8 minus 4 is multiple of 4. Therefore, for every 4, 8 belongs to R and 8, 4 is also belongs to R. Therefore, it is symmetric condition. Again, for checking transitive condition. Here consider 3 elements. 4, 8 belongs to R and 8, 12 belongs to R. That implies 4, 8 belongs to R because 4, 12 belongs to R because for difference of 4 minus 12 will be multiple of 4. Therefore, it is transitive. Hence, it is an equivalence relation. Hence, it is an equivalence relation. Now, check the condition for second question. That is, give an example, a relation which is symmetric, neither reflexive nor transitive. Here, I have to give an example. Only symmetric condition will be follows. Here, we know that the symmetric condition for every element of A is related to B and that implies B is also related to A. Here, consider the set A. Okay, here consider a set A. A is equals to 1, 2, 3 and relation. So, every element of A is related to B. 1 is related to 2. Again 2 is related to 1. 2 is related to 3. Then 3 is related to 2. Okay. This is an example for symmetric, neither reflexive nor transitive. Here 1 is related to 2 and 2 is related to 1. There is no 1, 1, 2, 2, 3, 3 here. Therefore, neither reflexive. Any transitive conditions here? Nothing. There is no transitive conditions possible. Second one condition is transitive but neither reflexive nor symmetric. The condition will be transitive but neither reflexive nor symmetric. Here the relation, have to write the relation R is equals to order pair A comma B such that A is always less than B. Here A is always less than B. This is the example for transitive but neither reflexive nor symmetric. Here have to consider, for example, 1, 2, 3. 1 comma 1 not possible because there is no equal symbol. Again for symmetric, 1 is less than 2 but 2 is not less than 1, hence nor symmetric. 1 is related to 2 and 2 is related to 3. Again have to consider 1 is always less than 3 only. Here transitive condition obeys. Again for reflexive and symmetric but not transitive. Reflexive and symmetric but not transitive. Here consider a relation R is equals to, here consider a relation R is equals to 1, 2, 3. Then it is reflexive. The set contain an elements 1, 2, 3. Here have to consider 1, 1, 2, 2, 3, 3 and 1, 2 and 2, 3. Okay. Now here the reflexive and symmetric condition but not transitive. 1, 1, 2, 2, 3, 3 is there, hence it is reflexive. 1, 2 and 2, 3 is there, hence it is 1, 2 and 2, 1. Okay, sorry, we have to take 2, 1. 1, 2, 2, 1. Here the condition, symmetric condition obeys. Okay, hence it is symmetric. Now check the condition. Now fourth one, reflexive and transitive but not symmetric. Here consider set A 1, 2, 3. Then the relation R is equals to, it is reflexive means 1, 1, 1, 2, 2 and 3, 3. But we have to show the transitive condition. Here for fourth one, reflexive and transitive but not symmetric. Have to consider 1, 2, 3. Then the relation 1, 1, 2, 2, 3, 3. It means it is reflexive. Then transitive 2, 3 and 3, 1 belongs to R. Hence 2, 1 is also belongs. Transitive condition obeys, but symmetric condition not obey. Here for fifth one question, symmetric and transitive but not reflexive. Other than reflexive condition, 1, 2 belongs to R and 2, 1 it is symmetric. Then 1, 2 belongs to R and 2, 3 belongs to R. Then third element 1, 3 which is also belongs to R. Here transitive condition satisfied, but there is no 1, 1, 2, 2 and 3, 3 elements here. Hence it is not a reflexive. Okay. Up to this the session will be going. Thank you.